Oh, perfect.
Now it's good.
Okay, so it's a pleasure to introduce Jay Wood, our second speaker today. He's from the Western Michigan University. He's going to talk about weights on mod MZ, and the MacWilliams identities. Please, Jay.
Good, thank you. Thank you very much for coming. Thank you for the invitation to speak in this session. I do mention finite fields somewhere in the talk, but mostly not. So I feel a little bit chagrined about that, but it's, I think, some material that a lot of people know something about, and I hope will be interesting to everyone. I also like to say how much I missed the opportunity to actually visit Buenos Aires in person, and I hope that sometime in the future, I and everyone else attending virtually will also be able to visit Buenos Aires in person. So a little bit of historical context on the MacWilliams identities. Jessie MacWilliams was a PhD student of Andy Gleason at Harvard, and her dissertation in 1962 included, as one of its parts, the MacWilliams identities. It also was published in a separate paper in 1963 called A Theorem on the Distribution of Weights in a Systematic Code. The context that MacWilliams was working in was with linear codes defined over finite fields, and she had dual codes, which are just given as the orthogonals under the standard dot product over the finite field. She was working with the Hamming weight, and she used the Hamming weight enumerator in her weight enumerators. So a few definitions. I hope most of these are familiar to people, but I include them for some completeness. I'll let F be a finite field, and then a linear code of length n is simply a linear subspace, usually called C, sitting inside of F to the n. So it's inside a particular n tuple space. So if you like, you can think of there's a preferred basis in a vector space, and then we're looking at linear subspaces inside of that vector space with a preferred basis. So it gives you particular coordinates for the code words. Then the dual code is defined using the standard dot product on F to the n. The dot product that is the same one we teach our calculus students, except that it's over a finite field rather than over the reals or the complexes. And when you have a linear code C, its dual code is defined to be all of those vectors which are orthogonal to the code vectors, where the orthogonality is with respect to this standard dot product. Now, of course, one of the ways in which this dot product over a finite field is different from the dot product over the real numbers is that it is that you don't have a notion of positive definiteness. So it's possible for a dual code to have a vector inside of itself, which is orthogonal to it. And there are, in fact, codes in which the code is equal to its dual code, and those are called self-dual codes. And those are a very important topic of research in coding theory. The standard dot product is, however, non-degenerate. And as a consequence, if the linear code has dimension k, then its dual code will have dimension n minus k, where n was the ambient dimension of the vector space in which the code resides. The Hamming weight defined on a finite field is very simple. It assigns a weight 0 to the 0 element of the field and assigns weight 1 to every other consequently non-zero element of the field. Those numbers 0 and 1 are to be thought of as integers, something that's in characteristic 0. We can then extend the Hamming weight to vectors, so elements of F to the n, simply by adding up the Hamming weight of the individual terms, of the individual components. As a consequence, well, I guess that's probably the next slide or subsequent slide. We go back a second. So the Hamming weight of a vector is simply counting the number of non-zero components in the vector. The addition of the addition on the right-hand side for the Hamming weight is an addition in the integers, and so that's a characteristic 0 sum, and we're just counting. The Hamming weight enumerator keeps track of the Hamming weights of all the code words in a linear code. So if you have a linear code C inside of f to the n, its Hamming weighted numerator is this polynomial in two variables, or at least one way to write it is as a polynomial in two variables, homogeneous of degree n, where the exponent on the y coefficient is the Hamming weight of a code word. And the exponent on the variable x is then sort of the complementary exponent, n minus the Hamming weight. And then you add that up over all code words in the code C. And of course, if two code words have the same weight, they will contribute two terms with the same variables. And so when you simplify the expression for the Hamming weighting numerator, you get a sum from 0 to n. So code words of having weight from weight 0 up to weight n. And the coefficient is the number of code words having a particular weight. And those are traditionally called A sub j's. So the MacWilliams identities relate the Hamming weighting numerator of a linear code with the Hamming weighting numerator of its dual code in terms of this particular formula, in terms of a linear substitution, so that the Hamming weighting numerator of the dual code as a polynomial in x and y is obtained from the Hamming weighting numerator of the original code using this linear substitution of variables. And then there's a scale factor on the outside given by the size of the code. So this theorem was the theorem that MacWilliams proved in the early 1960s. Now, since that time, there have been generalizations of MacWilliams identities. In particular, it's true over nice rings, and the technical term is Frobenius rings. It includes such rings as Z mod MZ, so integer residue rings. It includes many, many other rings as well. And you're welcome to talk to me later about some of those examples. One of the key features, and something I want to emphasize in the MacWilliams identities, is that the only thing that appeared here are the weighting numerators, not the codes themselves. So if you want to know the Hamming weighting numerator of the dual code, it's enough to know the Hamming weighting numerator of the original code. You don't need to know the specific details of the code. As long as you know how many code words have how much Hamming weight, that determines the same properties for the dual code. In fact, if you want to look at it in a slightly more fancy way, think of linear codes of a particular length and a particular dimension. Just look at all of them. Think of the set of all these linear codes of a fixed dimension and fixed length. That's where the C resides. And then think of taking its dual code, which will change the dimension, of course, from k to n minus k. So we have a map from associating to a linear code, its dual code. And then we can also take the Hamming weighted numerators of each of those. So the Hamming weighted numerator of the code, the Hamming weighted numerator of the dual code. And MacWilliams's theorem, the existence of the MacWilliams identities, says that there's actually a well-defined map between the polynomial spaces that completes this commutative diagram. Okay? So there's a well-defined map down here that allows you to complete this square. In technical details, this map is the map on polynomial rings induced by the linear substitution that we talked about earlier. There's an extra scale factor here, which accounts for the 1 over the size of C that occurred in the MacWilliams identities formula. Now, there are two ways of thinking about the Hamming weight of a vector. I've probably mentioned both of them already. So if you have a vector in f to the n, one way of thinking of the Hamming weight, which was the definition, was that we add up the values of the Hamming weight of the individual components. But a second way to look at it is in terms of partitions. So partition the field F into two classes. One of the classes is just 0, and the other class is all the non-zero elements of the field. And then you can also think of the Hamming weight as counting the number of entries in the vector that belong to each of these classes. So how many entries belong to the 0 class, how many entries belong to the non-zero class. Now, for the Hamming weight, those two definitions coincide. Okay? But it gives us a way to think about generalizing MacWilliams identities to other kinds of weights. In particular, the summand that occurred in the definition of the Hamming weight enumerator has the partition counts as the two exponents that appear. So some generalizations of the MacWilliams identities. Historically, there have been many successful generalizations, things like the complete weight enumerator and the symmetrized weight enumerators, that really make use of the partition and counting idea rather than the adding up weights idea. So the complete weight enumerator uses the partition, the finest partition available, 1-point classes. The symmetrized weight enumerators make use of groups of orbits of group actions and use those as the partition sets. Less well studied are weight enumerators that use a different weight, and then you add up the values of that weight on the components. So that's the other way of interpreting the weight enumerator of the Hamming weight enumerator, and that's what we're going to talk about in this talk. And perhaps one of the reasons it's not so well studied, or maybe will turn out to be a reason not to study it very much, is that the MacWilliams identities usually fail in these circumstances. And so I want to describe how that works. So suppose you have a weight, and you have it determines a weight enumerator by adding up values and counting how many code words you have with a particular weight. What does it mean for the MacWilliams identities to fail? So the MacWilliams identities will fail for a weight enumerator if there exist two linear codes, call them C and D, such that the codes have the same weight enumerator, but their dual codes have different weight enumerators. Now, how can you tell if two weight enumerators are different? Well, for that, all you need to do is to show that the coefficients of the, say, the jth term are different. So if C perp and D perp have a different number of code words of weight J for some J, that's enough to say that the two codes do not have the same weight enumerator. So if this situation happens, where you have two codes with the same weight enumerator, but dual codes have different weight enumerators, then there's no way to complete with a well-defined map the commutative diagram that I had shown before. You go back to that diagram for just a second. There we go. So if we have a different type of weight enumerator, and you cannot fill in, if you cannot fill in this part of the arrow, then there is no MacWilliams identities. So if you have two codes here that go to the same place here, but go to different places when you take their duals, then there's no way to fill in across. So you don't have a well-defined transformation. So let's talk a little bit more about details of having weights and weights enumerators for generalized weights. So suppose we have an integer valued weight on a finite ring. So Hamming weight's a perfectly good example, but we'll get to some other examples in a minute. You can extend W to a weight on R to the n by simply adding up the weights of the individual components. Okay, so it's exactly what we did for the Hamming weight, and it works for many other situations as well. In the formula, I'm going to need the maximum value of W over R and refer to that as W max. So then the weight enumerator is just determined like we wrote down for the Hamming weight. Sum over the code, look at Y to the weight of the code word. And remember, the weight of the code word is the sum of the weights of the individual components added up over the code word. And then X has a complementary dimension, complementary exponent. And the number that appears first is, well, if every entry had maximum value, then the largest value of the weight for a vector would be n times the maximum value at the entries. So this is just to fix the degree of this homogeneous polynomial. In some examples, I'm just going to save some space and write this in terms of one variable rather than two, and just use t to the wc added up over the code. And in the next slide, I'm going to show at least 4 different weights, one of which is the Hamming weight. They will each have a weighting numerator assigned to them, and the letters just correspond. So H gives you an H weighting numerator, L gives you an L weighting numerator, etc. So here are some examples over an integer residue ring, Z mod MZ. These are the sort of the 4 well-known weights that I'm most familiar with. There may be more. First one is the Hamming weight, which we have already seen. So when it's everything is equal to 0, it's 0. And for the Hamming weight, any non-zero entry has Hamming weight 1. And then you add up over all the components of a code word. The second example is called the Lie weight. And if you think of the integers mod m in symmetric form, so by that I mean 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on, so symmetric about 0, then the Lie weight is just the ordinary absolute value. So just take the positive part of it. The Euclidean weight is just the square of the Lie weight. And then there's another one called the homogeneous weight, which I will give some details in later slides. Okay, so these are certainly the Hamming weight, Lie weight, and Euclidean weight are well known and well used in coding theory. The homogeneous weight is newer and it is becoming increasingly important. What's the status of MacWilliams identities for these weighting numerators, these weights, and then the weighting numerators assigned to them? Well, for the Hamming weight, MacWilliams proved that it's true for all, well, MacWilliams proves this for finite fields, and then subsequent work has shown that it's true for every M. So all these Z mod MZs, it's true for every M. For the Lie weight, it's true for M equals 2 and 3 for an easy reason, namely that when M is 2 or 3, the Hamming weight, the Lie weight is equal to the Hamming weight. It's also true for M equals 4. And this appeared in, among other places, the famous 5-author paper on Z4 codes by Hammonds and the rest. For Euclidean weight, MacWilliams identities are true for M equals 2 and 3. And again, for a trivial reason, namely the Euclidean weight is equal to the Hamming weight in those cases. For the homogeneous weight, I haven't defined it yet, but I can tell you that when M is a prime, then the homogeneous weight is just a scalar multiple of the Hamming weight. And so MacWilliams identities hold by virtue of them holding for the Hamming weight. But there's one other case when M equals 4 in which they are true. And in that situation, the homogeneous weight is the same as the Lie weight. And so this bold-faced 4 is to match with the bold-faced 4 coming from the Hammonds paper. So there are situations where the MacWilliams identities hold for these other weights. And so far, it's by virtue of them equaling the Hamming weight by and large. So here again, the 4 weights. And to see what they are explicitly over Z mod 6, here's a little table of values. Hamming weight, of course, for every one of them, the weight of 0 is 0. Excuse me. And for the Hamming weight, the weight's always equal to 1 for the non-zero elements of the ring. The Lie weight is the absolute value of the entry, so 1, 2, or 3. Euclidean weight is the square of the Lie weight, so 1, 4, and 9. And now here's the homogeneous weight. And I think so it's 1, 3, and 4, and I'll explain why those are in just a minute. But let's for the moment just say, just agree that this weight is 1, 3, and 4. And now let's look at 2 codes over Z mod 6 generated by, one case by 111, and there are the 6 code words, just the basic repetition code. And another code generated by 133. And if you do all the multiples, you get these numbers. What are the weighting numerators of these 2 codes? Well, all you have to do is figure out the weights of each of these code words by adding up the homogeneous weight for all the entries. We can do these quickly. This is 0 plus 0 plus 0, so that's 0. This one is 3 This one, each 2 contributes a weight of 3. So 3 times 3 is 9. This one gives you 12. This one gives you 9, and this one gives you 3. Now, on this one, again, 0, 3 has weight 4. So we have a 4 plus 4 plus 1. So there's a 9, 3, 12, 3, and 9. So they actually have the same weighting numerators. 2 code words of weight 3, 2 code words of weight 9, 1 code word of weight 12. But notice when we look at the code words, here's say the generator is 111. The generator and its negative had weight 3, and then the 2 and the negative 2 had the weight 9. Whereas for the other code, the generator has weight 9, the 133 and the 533, and the 2 and the -2 have weight 3. So the positions, in some sense, of where the weight 3 vectors lived versus where the weight 9 vectors lived have been swapped in these 2 codes. Now, what about the dual codes? Well, I've worked out the dual code for the first one, and I think that everyone is capable of working out the dual code for the second one. But you can do it by hand, and then you can again count what the weights are for all of these things and add them up. And so here's a repeat that for the homogeneous weight, code 1 and code 2 had the same weighting numerator, whereas for the dual codes, they turn out to have different weighting numerators. Here at code words of weight 2, there are 6 of them for the first code, but only 4 of them for the second code. So this is the first example of a failure of the MacWilliams identities. There's no way the MacWilliams identities can hold, because if you had such a formula, then these counterexamples would not be possible. Now, more generally, this is an example with the Lie weight, and comes from a paper that I wrote with a former student of mine, Noha Abdelghani. For the Lie weight over Z mod 6, you can look at, now these codes don't look all that different from the ones we just did. So a code generated by 4 ones, and then one generated by 1133. And if you carry out the same type of computation, you can show that the Lie weight enumerator for each of those codes is the same, whereas the Lie weight enumerator of their dual codes are different. And again, they differ at code words of weight 2. And for the Euclidean weight, even over Z mod 4, here's the Euclidean weight for Z mod 4, 0, 1, and 4. You can take code generated by 11122, or you can take a code generated by 2 vectors, 0, 0, 0, 2, 2, 2, and 0, 2, 2, 2, 2, and 0. Generate those codes, figure out the Hamming weights, or sorry, not the Hamming weights, the Euclidean weights. And again, the Euclidean weight enumerators are the same, but the dual weight enumerators are different. And in the case, if we go back a slide, you'll notice that in the generator matrix for the C6, there's a 0 column. So that means that the vector 1, 0, 0, 0, 0, 0 is a dual vector for this code. And that has weight 1. That accounts for it, and its negative account for this entry, the 2t entry. And whereas there's no singleton vector that annihilates the other code. So this one is actually very simple to figure out. Okay, so a little summary of the examples so far. For the Lie, Euclidean, and homogeneous weight enumerators, there exist linear codes whose weight enumerators are the same, but their dual codes have different weighting numerators. Now some general results. So for the Lie weight over Z mod MZ, this paper I referred to a couple slides back by Noha and myself, says that that theorem works in general, that for every m greater than or equal to 5, you can find examples of codes which have the same Lie weight enumerator, but their dual codes have different Lie weight enumerators. And again, remember the reason we need m greater than or equal to 5 is that we know that when m is equal to 2, 3, or 4, that the theorem is true, that MacWilliams identities hold. Talked about that earlier. For the Euclidean weight, this is the one that's turning out to be harder. I don't have a general theorem, but I have lots of computational results. For any m divisible by 4, by 6, by 9, or by a prime in the range of 5 up to, and it's like how far I wanted to run the computer program. I stopped at 2 to the 13th. So in all of these situations, you can find two codes with the same Euclidean weighting numerator, but whose dual codes have different weighting numerators. Conjecture, of course, is that you can always do that for any m greater than or equal to 4. For the homogeneous weight, if m is at least 6, but not prime, then you can find examples for which the MacWilliams identities fail. And that's we're going to talk about for the rest of the talk, primarily. And again, the reason why you have to omit primes is because the homogeneous weight is essentially the Hamming weight when you have primes. And then you have to eliminate 4 because of the Lie weight equivalence. And then recently I was able to show that the homogeneous weight fails for matrix rings, provided that, so for 2 by 2 matrix rings, provided that the Q in the coefficient field is bigger than 2. It turns out to hold for 2 by 2 matrices over F2. All right, so now let's talk about in some detail the homogeneous weight. Over Z mod MZ, this was defined by Constantinescu and Heise, 1997. And then Honalt, Nechayev, and Greferath and Schmidt did work over general finite rings. One way to characterize the homogeneous weight is that the weight of the 0 element is 0. That's 1. Secondly, that the homogeneous weight is constant on any left orbit of the group of units. So associates should have the same homogeneous weight. And the real kicker is that if you look at the average weight over any non-zero left principal ideal, the average weight should be the same. So take a non-zero left principal ideal, sum up the values of homogeneous weight over all those elements, and divide by the number of elements in the ideal. That number should be the same for all these non-zero ideals. Greferath and Schmidt actually give you a formula for this in terms of Mobius functions. In particular, that formula says that the homogeneous weight exists for any finite ring with 1, and that it's unique up to a scalar multiple, up to a uniform scaling. Some details, I mentioned this earlier, over a finite field, any scalar multiple of the Hamming weight is a homogeneous weight. The reason is that there are so few ideals in a finite field. So for example, if you can choose, of course, W of 0 has to be 0, but if you take W of R equal to Q, the size of the field, that will give you a homogeneous weight with average weight Q minus 1. With that scaling, everything is an integer. The next most, well, the Z mod MZs, the next most complicated after fields is Z mod of prime power. There are the ideals, they form a chain. This is an example of a chain ring. And if you set zeta equal to P minus 1, so which means that zeta plus 1 is equal to P. So 0 has weight 0. Everything else in the ideal generated by P to the A minus 1 has weight P. And then everything else above that, not in this socle, has weight P minus 1. And if you figure that, you work those out, the average weight over any non-zero ideal is P minus 1. You can work with, and I'll just do 2 primes quickly. If you're working with Z mod M, where M is a product of 2 primes, or 2 prime powers, the zeta that you can use is P minus 1 times Q minus 1. And this then gives you the description of what the values of the homogeneous weight is on any particular element of the ring. Okay? It depends upon what happens down near the bottom of the ring. 0 at the bottom, and then just basically you're looking at the socle of this ring, and that's where all the complications lie. Anything outside of the socle has a homogeneous weight equal to this average value of zeta. And the reason I choose this particular value of zeta is so that all of these numbers turn out to be integers. So that you can then use them as exponents in polynomials without complications. There are a couple of useful features of the homogeneous weight. Now there's a formula. It's a little messy. You can just sort of write it down, but it's a little complicated. But one feature that we used in the previous slide is that you can always choose the average weight in such a way as to clear denominators and have integer values. And so for a general M written as a product of powers of primes, that choice of zeta is just the product of prime minus 1 over all of those primes. At some point, I'm going to slyly sneak in an equal sign in some subsequent slide that depends upon knowing what happens when you change modulus. So if you're working over Z mod M1 and you multiply everything in sight by M2 and think of the numbers over Z mod M1 times M2, then what happens to the homogeneous weight? And well, the nice feature is that it scales uniformly by a constant. The constant does not depend on the R in question. Okay? So there's some compatibility between the homogeneous weights for different values of the modulus M. All right, once you have the homogeneous weight on Z mod MZ, you can then extend it to vectors like we've seen for the other weight enumerators. Simply add up the homogeneous weights of the individual entries. And then if you have a code, you have a submodule of Z mod M to the N, you can sum over all the code words and take T to the homogeneous weight, and that gives you a homogeneous weight enumerator. And so now the statement of the main theorem is that if we assume that the modulus M is not a prime and that it's at least 6, so if it's not a prime, that we're leaving out 4 by doing this, as well as the primes, then there exist linear codes C and D over Z mod MZ with the same homogeneous weight enumerator, but whose dual codes have a different number of code words for some weight. So in particular, the homogeneous weight enumerator of the dual codes are different. So once again, in terms of the commutative diagram, here we have linear codes over Z mod M of a particular size. Their dual codes will have a complementary size. We cannot fill in the dotted arrow connecting homogeneous weight enumerators of the original code to the homogeneous weight enumerators of the dual code. There's no well-defined map that does this because there are examples on the left that give you the same result, but their dual codes give you different results. So no MacWilliams identities for M's greater than or equal to 6 and not prime. So what do the examples look like? So those of you that my slides are already posted, sorry about that. My slides are posted. If you want to work out some of these by hand, you're welcome to do it. The computations are not that difficult. So over Z mod P to the A at least 2. So we're not in a finite field. So here's the first generated matrix has a P to the A minus 1 in the first entry, and then all the rest of them are P to the A minus 2s. The total length is P plus 1, so there's 1 in the first slot, and there are P terms, each entry of which is P to the A minus 2. The other generator matrix has only P to the A minus 1 in their powers, and we're really, if you like, you can think of this as sort of the lines in a two-dimensional vector space. So here's one of slope 0, and here's slope infinity, and all the other slopes in between. So 0, and then all these P to the A minus 1s on top. On the bottom, a p to the a minus 1, a 0. And now the rest of these terms are all the multiples of p to the a minus 1. So here's the multiple of 0, multiple of 1, multiple of 2, up through a multiple of p minus 1. So as an exercise, you can show that all of the non-zero code words in those two codes have the same weight. They all have weight p squared, and they're p squared minus 1 of those non-zero vectors. If we want to look at the dual code, we'll look at singleton vectors. A singleton vector is a vector with exactly one non-zero entry. And those are the vectors that usually have the smallest homogeneous weight. So you can look for a singleton vector where its non-zero entry annihilates a column. So if we go back for a second, if you multiply p to the a minus 1 by p, that will annihilate this column. Here you have to multiply by at least p squared in order to annihilate. So you can work through the situations of a couple of situations. If p is at least 3 and a is equal to 2, then you can find a singleton vector with weight p that will kill off p minus 1. So it'd be p minus 1 such vectors that annihilate the first code, but a different number that will annihilate the second code. And in the situation where p is at least 2, but a is greater than or equal to 3, then you can look at vectors of singleton vectors with an entry of weight p minus 1, and again annihilates a different number of columns in those respective matrices. There's one case that we've skipped, which was the case when p is equal to 2 and a is equal to 2. When p is equal to 2, the homogeneous weight has values 1 and 2. And so there are doubleton vectors that can have weight 2, have 2 1s. And that actually crops up in the case when m equals 4 and allows you to, so here we think we have different numbers, and we do at this point, but these are only from singleton vectors. Doubleton vectors will close the gap on this, and the code counts are actually the same. All right, let's look at case of 2 primes. So for Z mod PQ with P less than Q. So here's one example of a one generator matrix. So in the first column, Q and P, the rest of on the left-hand side in the first row is a bunch of 1s. And down below it are multiples of P. So there are Q of those. They go from 0 up to Q minus 1 times P. Then a Q0 in the middle. And then on the right-hand side, 0 and then P's across the rest, then a P, and then here all the possible multiples of P, all the possible multiples of P. So in a way, if I go back a few slides, it's reminiscent of this type of construction. I've grouped them with putting these vertical lines in place. It just indicates what the GCD of the entries are. So here, this has GCD1, the middle it has GCDQ, and on the right has GCDP. All of the entries in the second row are multiples of P. So you look at the linear code that's generated by this matrix. Think of taking a vector of size 2 on the left and multiplying against this matrix, generator matrix. So you're taking linear combinations of the rows. And because all the second row is multiple of P, Q will annihilate the second row. So the size of this code is P times Q squared. Again, a computation shows that the homogeneous weights for this code, of course, the 0 vector has weight 0, but all the other vectors have one of 3 possible weights, alpha, beta, and gamma. And we count how many vectors there are with those weights and what the coefficients give you. And here are the explicit values for those weights. And when P is equal to 2, the beta and the alpha coalesce and the weighted numerator equation consolidates. Now, when we talked about some of the earliest examples, we had over Z mod 6, we had 111 and we had 133. And we went through them and said, oh, the 1 and the 5 gave you one weight and the 2 and the 4 gave you a different weight. And for the other code, those things were reversed. Okay? So we're going to do a similar sort of orbit analysis. The group of units of Z mod PQ acts on the linear code by scalar multiplication. So think of a unit times the message bits that go into the linear combination. If you think of that as a group action and look at its orbits, those orbits are represented by the same types of expressions that appeared in the columns of the matrix G. Just think of the transposes of those columns. And we'll, again, think of those in terms of groupings. So you could have something with a unit and a multiple of P, or you can have Q and 0, or you could have P and a multiple of P. And recall, this is what the homogeneous weight enumerator was for the example that we gave. The P-1 code words that appear with, with exponent beta, those come from one orbit, namely the orbit in the middle, grouping 2. The Q² - 1 code words that have weight gamma correspond to Q+1 orbits, each of size Q-1. So this is built up of a bunch of different orbits but all the orbits have the same size. And the last term with exponent alpha, with weight alpha, those P-1, Q² - 1 code words come from Q+1 orbits of size P-1, Q-1, corresponding to the left grouping. So second grouping, third grouping, and first grouping. Now we're going to build a second code. So the code we just talked about, if you think of what's the listing of its weights, you have a bunch of alphas, you have corresponding to group 1, a beta in group 2, and then gammas in group 3. Each of these alphas represents an orbit of size P-1, Q-1. Each of the gammas represents an orbit of size Q-1. So if you take one sort of alpha orbit, that counts the same as P-1 of the gamma orbits. And so we make a flip, we swap things. And so we replace one alpha orbit by gamma and replace a bunch of gamma orbits by P-1 alphas. So we're basically saying we would like to have a code with particular weights at particular locations on particular orbits. And this is perhaps one of these cartoons that have this big blackboard full of all sorts of complicated expressions, and then it says, and a miracle happens. So the miracle here is that the second code exists. If we make this switching of the locations of where the weights live, there actually is a code that accomplishes that. Now, this is covering a lot of, I'm hiding a lot under the rug. There's a map that associates the multiplicities of columns in a generated matrix to the orbit weight listing. Let me go back a second. It was the generated matrix G. So we're just, now you could imagine, well, what if I took a different generator matrix? Suppose I had a generator matrix that didn't have just one column with this Q and P. Suppose it had 5 columns like that. And maybe it has 10 columns of these instead. What are the weights of code words then? Well, you can figure that out, and that's just a linear transformation. So that there's a linear transformation that keeps track of multiplicities of columns and spits out the listings of the weights of orbits. That linear transformation for the situation of homogeneous weights has an explicit inverse. You can explicitly find the inverse to it. And for the swapping of orbits that I talked about, when you take the inverse, you get non-negative multiplicities for the second code. And that's you get rational numbers, and if you clear denominators, you then have non-negative integer solutions. And that means that you can use those non-negative integer solutions as multiplicities and build a generator matrix. So you can actually clear denominators by using p minus 1 times q squared. And when you then compare the multiplicities for the two codes, you find that the multiplicities in grouping 3, the sum of the multiplicities in grouping 3 are the same, but the sum in grouping 2 are different, and the overall sum is the same. And these words, the same here, different here, will be important. So I'll ask you to remember them. And now I want to tell you what happens in general. So I see that I'm running out of time, so I'm going to pick up the pace a little bit. So a general M, product of a bunch of primes. We've already done the prime power case. And in fact, we've already done the 2' case. So we've certainly done the prime power case. So assume that k is at least 2. Then pick 2 of the primes, and then use the results we just did for 2 primes to build 2 generator matrices like we just did, C and D. Once we have those matrices over using 2 of the primes with prime powers, multiply all the entries by the rest of the primes that are involved with M. That then gives you generator matrices over the big ring Z mod MZ. And the 2 codes will still have the same weighted enumerators. We built them in the 2' case to have the same weighted enumerators. When we scale them up, they will still have the same weighted enumerators. That's what I referred to earlier when you change modulus, that the weights scale uniformly. Now we have to analyze the dual codes. We've gotten 2 codes whose homogeneous weighted enumerators are the same. Are there dual codes? Do those dual codes have different weighted enumerators? So with one important exception, when m equals 6, we only need to look at singleton vectors, vectors that have one non-zero entry. And we look for singletons that annihilate the column where that non-zero entry lives in the generator matrices of C and D. Now, what can singletons do? Well, if the singleton is a unit, it's not going to annihilate anything. Units don't annihilate things. If you have this, if the singleton entry is divisible by P, but not divisible by Q, then it's going to annihilate only columns in grouping 2. If it has divisible by Q, but not by P, then it's going to annihilate only columns in grouping 3. And if it's a multiple of both, well, then it annihilates everything. Okay, so notice there's nothing that annihilates column 1 only. So it's 2, 3, or everything. And we showed earlier that, or we mentioned that, that if, when we did the C and the D matrix, that the multiplicities in grouping 2 were different. And so singletons that annihilate grouping 2 columns will contribute differently to the weighted enumerators. All the other singletons are in the other classes, either grouping 3 columns, but the sum of multiplicities there were the same, or they annihilate everything, and the sum of multiplicity in all columns were also the same. Of course, if you don't annihilate anything, then you contribute 0. So singletons that annihilate grouping 2 contribute differently. All the other singletons contribute the same. And part of the analysis says that you can always find singletons that annihilate grouping 2 columns only. And that's what proves the theorem. Now, of course, there's a little asterisk there where I say, what, always? Well, almost always. There are situations like when m equals 6 that require special arguments, but I won't do that today. Let me close with an example. When m is equal to 15, the primes are 3 and 5. You look at 3 minus 1, which is 2, 5 minus 1, which is 4, so zeta is 8. And here's a listing of the homogeneous weights by orbit, so 0, 7, 10, and 12. Here's the generator matrix G. So here's Q and P, and here's 1s, and here are the multiples of P, and so on. So there's explicit matrix. And when you look at all the code words generated by this matrix, here's the homogeneous weighting numerator. So 2 code words of weight 84, 24 code words of weight 100, and 48 code words of weight 109. When you find this D matrix, you can clear denominators by using 50. For the code word C, all these columns are repeated 50 times. For D, the same columns are used, but repeated at a different number of times. And particularly the middle grouping, grouping 2, is repeated only 32 times. The common weighting numerator is now, the weights are much bigger, but the same distributions that we had before. And because 32 is different from 50, you can show that the things that annihilate the middle column, which are multiples of 3, there are 200 of them for the first code, but 128 of them for the second code. So those code words, those numbers of code words are different, and we have a counterexample to the MacWilliams identities. All right, I think that's a good place for me to stop. I want to, on behalf of myself and all the other speakers, thank our session chairs for organizing the session. And I thank all of you who participated. Thank you for your attention. Thank you very much.